You know, but what is the next step? Because then you have to go out. Otherwise, you are still, you know,
his
what is the next step? The jump, like to the next level. Think is not there.
I mean,
What is the next
translation.
step?
I mean,
Like everyone has done.
dress like you're beauty.
I have too much.
You watch with your eyes.
What is
No.
Ni por el COVID.
Opcional.
No. I don't know.
Okay.
9.
One hello from just
7.
Here we go. Hey, do you want to?
Yeah, but I did time yesterday.
Okay, you told me no.
Yeah, but I don't have.
Okay, don't worry.
Tomorrow?
Tomorrow, of course.
Where's your beard?
Right away.
You're not a good scientist.
Yeah, what happened here?
Really?
Who made this to you, man? You have to take revenge for this. Estoy imaginando que hubo unas personas en la calle que la agarraron y la pitaron.
Nothing is a small thing.
Someone took notes?
Yes, in a
Yeah.
way. I just took some of them, but he was
One over 8.
and with him throughout, like we didn't.
What do you mean by one?
Wait, so no one goes.
No.
Thank God.
Okay. If the observer has
It's gonna be the best sessions in my
if the
life.
observer has 10 meter square acceleration,
Is he good?
0.1.
Sorry?
Is he good?
Yes, he's
Empezados primates,
but you have to be advanced.
y siempre funcionaron.
I think you've already solved those problems.
See,
And
I
then
didn't know it's
maybe again.
Bueno,
But
estábamos
maybe there may be problems that you couldn't do.
Sí, cuando todavía no sabíamos cómo dominar el juego, hacíamos esto para pasar.
What do we have Venn diagram?
What? These are not Venn diagrams. These are manifolds.
Oh.
When we say that
And vector bundles. But if you
So it
want
doesn't look it.
He loves this.
There is no way that is true.
I think that about this. Then why is it? But everyone says.
He loves that he doesn't have the problem.
Oh, he's only guy. Because she's a girl. Because she's a girl. Yes. Exactly. That was weird.
Eso que tenía una amiga que cuando estaba en el tatuaba la boca me decía, era como que
We all hate him.
No, I don't hate him.
No, okay, we all don't like him.
Yeah,
I hate him, but I don't want him. And he loves
No, it's just I'm asking about some other stuff.
we all did that. Still.
estaba pasando algún problema de su...
Here you go.
So I brought it up.
Yes. Stationary.
There's only one page of one unspoiled page. I'm going to fit everything that
You can do it.
Oh my god, man.
You need stuff.
Oh no, is that possible?
He's sharp in his mind. Don't get
But did it happen? Did it happen like your phone that he missed time?
There are no certain. Dove ma non a che te no?
A 40.
Al palo.
But you should show it to a mechanic or something. I mean, what's the problem?
Okay. Sometimes when I wake up, the apps just update stuff.
Why is it from Microsoft?
No.
Yes.
Maybe it's just
No.
No.
It's stuck inside.
He doesn't even know that it's phone.
I got it like 4 months ago. The day before, like.
In 4 months, he couldn't realize that his phone is whether a Microsoft or an Android. No, it's an iOS.
Oh my god. I think your phone is stuck into that and doesn't know where you are.
He doesn't know what the operating
Like,
system of his phone.
really?
It's Android. Really? It's Android.
Okay.
Really?
Okay. Then why is it creating a So you're taking the class?
Yes. No. Yeah, I'm going to take the question.
Come on. Very good.
I'm nothing for certificate.
Why did you buy these pages?
Because it's guaranteed. Geometry. Convenient. I want to change. I want to change, that's it.
Okay. But why were you giving the excuse general relative?
Okay, I bought this one.
Space time.
Okay.
The fabric of space time. You wanna stay there?
Do you have eyes on the back of your
Really? You're gonna do the class like this?
No.
question? Okay, so today we are going to talk about the variation principle and symmetries and nodal theorem. I asked Giovanni, he said that he has already talked about this topic. But anyway, I'm going to review it. I might get a bit distracted if you sit like that.
What?
How to do what?
Okay, so let's start with a simple example of variation principle. So the general idea is that we use the Lagrangian method to describe dynamics So there was Newtonian and mechanics and Lagrangian mechanics. They were giving the same results for the classical dynamics, but in modern physics, the Lagrangian mechanics was the one that was the right framework to do to generalize it to relativity and quantum mechanics. So that's why we do Lagrangian mechanics, and the Lagrangian mechanics is based on variation principle. So now we want to talk about fields. So what do we do when we want to use Lagrangian mechanics or Lagrangian field theory? We are talking about field, some field phi, and write an action for this field phi, which is an integral over the whole space-time. Now imagine I have a scalar field with some potential. Then we write an action for this scalar field. And the way that we derive the equations of motion is that we require this action to be stationary under variations, keeping fixed the boundary conditions. So we send phi to phi plus some arbitrary delta phi with the only condition that delta phi vanishes at the boundaries when we impose the boundary condition. And then we ask what is the variation of the action under this. So we basically look at S of phi plus delta phi. We plug this change in the action, and we keep linearizing delta phi. So if I linearize in delta phi, what I get is d mu phi, d mu. Well, let's only look at the variation. So there will be a zeroth order term in delta phi, which is basically what I started with, and there will be variation. So this is one of the terms, and the other one is v prime times delta phi. What is the potential comes with the negative sign. And then we can do integration by parts here using the fact that the delta phi vanishes at the boundary. So this term can be written as d4x. If I do integration by parts, then I get delta phi times eta mu nu d mu phi minus v prime plus a term plus a boundary term. So some integral over the boundary of the space-time times delta phi times d mu of phi. So this is a three-dimensional integral, and this psi mu is the area element on the boundary. So this integral, since it is at the boundary, when I send x to infinity, so here I assume that I'm integrating over the whole space-time. Since I'm sending x to infinity, since we assume, so there was this assumption here, delta phi, when x goes to infinity is equal to 0. So that assumption tells me that this term is 0. So we get this term, and then if I require that the action is stationary under this variation, what multiplies delta phi has to vanish. So for arbitrary delta phi, this integral has to vanish since delta phi is arbitrary. This factor has to vanish identically. And so that implies, that gives me the Klein-Gordon equation, or the equation of motion for a scalar field in a potential. Another example that we can, is there any question here? So this probably I've seen, we can move a bit faster so we can consider the point particle action. There is a particle that moves in a space-time, it has a position, it has a trajectory in a space-time. So remember we had word lines in a space-time. So this was x0 and this is, for instance, x1. And the word line it was a set of points. So we could parameterize this word line by one single parameter. I'm going to call it sigma, the parameter along this. So there is some trajectory, x mu of sigma. So we can write a point particle action, which is integral d sigma times the square root of eta mu nu, or minus eta mu nu, dx mu d sigma, dx mu d sigma. So this might be familiar if this x mu is just the trajectory of this time-like observer, then this integral is basically the integral over the length element, the invariant length element along this curve. So if I plug back the actual trajectory, we get the length of this action is m times the length of proper time of the observer. Of course, when we write the action, the variable that sits in the action, it doesn't have to be the solution of the equations of motion. The whole point of writing the action is to derive the equations of motion from this. So a priori, these phi's are just arbitrary variable, also this x. So by requiring that the action is stationary, we find the data trajectory that satisfies the equations of motion. So how do we do it again? Basically we repeat the same exercise. Now the variables are in this integral are x mu fields. So in 3 plus 1 dimension, there are 4 fields x mu that I take them to be x mu. I change them, so do a small variation, and again require that the action is stationary under this variation. So require that delta S is 0. So what is a delta S? It is given by integral d sigma. So I should do the variation of that. It gives me 1 over square root of minus eta mu nu dx mu d sigma dx mu d sigma times where I use the symmetry of eta mu nu. So there are two terms, but they are the same. And there is a minus sign. Now again, I do the same thing as before. I do an integration by parts in this term. So that gives me m d sigma times delta x mu times d by d sigma of eta mu nu dx nu d sigma divided by a square root of minus. Let's put some other in this row. What are the other indices? Lambda rho. This rho is sigma dx lambda is sigma. Plus a boundary term, which we can again ignore because we assume that the variation vanishes at the boundaries of the integration. And again, since delta x mu should be arbitrary, what multiplies it has to vanish, and that gives us the equation of motion. So d by d sigma eta mu nu dx nu d sigma divided by the square root of minus eta mu dx. No, that whole quantity has to vanish. Okay, now I can define we can define the proper time theta squared, or we have already defined it. It was minus eta mu nu dx mu. So this object that appears here in the denominator, that is square root of minus eta mu nu dx mu dx sigma dx mu. This sigma, this is nothing but d tau d sigma. So if I use that in this equation and also multiply the whole thing by 1 over this square root, the equation becomes d squared d tau squared of x mu is equal to 0, which is the familiar equation that we wrote before. So before we wrote the relativistic analog of the Newton's second law. It was it was acceleration equals to force. Here I haven't had any potential term for the particle, so the force is 0, and I basically get the acceleration should vanish. Note that since eta mu nu is constant, this is equivalent to the other version of the equation that we wrote before. So the other, so this is eta mu nu. Sorry, but my definition of x mu with lower indices is just eta mu nu times x mu, but eta mu nu is constant. So that also implies that x mu with upper indices is 0. Okay. Any questions about this?
Why is that the action for the relativity case?
Say it again.
What is that? Why is that the action in the relativity case?
Why is this the action?
Yes.
But there are various ways of justifying this action. Maybe the easiest one is that because it gives you the right equation of motion. A deeper way of understanding it is that that is that is the lowest derivative invariant term that one can write for the action. So when you write an action, this is the principle that we follow in particle physics. When we consider some theory, when we are trying to write a theory for a field or for some variable, some degree of freedom, then the principle that we follow is that we try to write the most general action that describes that degree of freedom, and then use experiments to constrain that action. Now, usually when you try to write the most general action for some field or some degree of freedom, that most general object is not a finite thing. There will be infinite number of possibilities that you can consider. But then there are other criteria which determine what term is more important compared to the other term. For instance, if you are doing experiments with some finite energy, the lowest derivative terms that appear in that action are the most important one. So now if you are trying to write some action for a particle with this coordinate, the principle tells us that we have to write the most general action, which is some scalar quantity or an integral over a scalar quantity, and this is the lowest derivative term that I can write. That satisfies the symmetries of the problem.
And like something related about the proper time, like you want to maximize or find extremize the proper time or something, because that is the part.
Yeah, that is essentially what this action does.
Because that I mean the proper time is like the length or something that your trajectory is. So you want to extremize it, something like that.
Yeah, this integral is exactly the length of the trajectory. So when I extremize it, I am extremizing the length of the trajectory. However, if you have some other terms, some other forces, then it's not necessarily the case that the particle moves on the trajectory with the extremal length. That's exactly what we want to consider now. Now imagine we add to this point particle action, we add, suppose the particle is charged and it's moving in some background electromagnetic field A mu. So then we can add another term to this action, which is an integral of the charge of the particle, d sigma dx mu d sigma times A mu. And now we can ask the same question: what is the equations of motion that follow from this action? Which is your exercise now. So see if it gives you something familiar.
logs.
I'm not getting the answers in the other one. The should be F me. But I'm not getting that. Yeah, change it. But I should get another, yeah, I should get another. to get the F from.
Yes, yes, this is correct. So let's remember coefficient. So what are lambda? Because a mu, again the same thing, a mu is a function of x. So when you do variation, there will be
There will be a
another
variation
thing.
in, okay.
Because a different. So delta x mu is delta x mu. That's different. But delta a is going to be had delta a because a is a function of x. Right? So we have done a variation of x, but we know if a of x plus delta x, we can, if delta x is a span, we can Taylor span. So you get that. So what happened?
I forgot the start.
Although I don't see very clearly.
Yes, I did it here, but I didn't understand. I put it very A, so I just do it very quickly in here. So I just so the answer is right?
Answer is right.
Okay.
After time.
Yes, yes.
I cannot reach the people in the middle. We have
No, still in this area. I'm multiplying by this one. I will get this one.
so this is correct.
Do it done by that. This is done.
Where is
This and boundary can do.
right?
And that's the same thing. This like this.
No, sorry, I don't understand. So this one you are going to do an integration by parts, right?
I want this one plus this one.
No, but how? If you do integration by parts, you get derivative of a mu, no?
Yes.
You are talking about it.
Yes, I equal to get delta A.
Wow. If I do integration by parts, the d by d sigma of something times something else. If I do by parts, I get minus the first term times derivative of the second. So there should be d by d sigma of a mu.
Yes.
Varying the equation.
Yes.
Use the
Did you define
yes. I was thinking of A being fixed, but so yeah, I was missing the dependence on X.
Yeah.
Yeah, we're not making A dynamical, but still depends on it.
Yeah.
I made a variation of both. I mean this term and a variation of this term.
Right.
So A mu del X mu del X. But these two indices are different.
Yes, they are different.
So how can I make it the same so that I can pull it out and get the zero there? Because if I multiply
this new index is summed over, right? So we call it a dummy index.
right?
You can call mu something else. You can call it mu or sigma or something else.
Yes.
Also here, this is a dummy index. So you can call them the same thing.
I see. Okay.
And then you factor it out.
I see. Okay.
Are you getting? Only person that I cannot reach is Alejandro. Yes, that is correct. And then what should we do? So the first term is similar to what we had several times. We try to take when we have derivatives of our variations, we do integration by parts to put it on the other. Another question is what to do with the second term. So the second term is changing because we have delta A because A is a function of X, right? So it's A of X plus delta X. So we can Taylor expand it.
Got this equation.
Yes, but now we wanted to do something about dA by d sigma, right?
Yes.
So what happened to dA by d sigma?
We can use the chain rule.
Right.
X and then.
Then it did something.
Oh.
Something nice.
Familiar.
Yeah. Okay, let me do it. Yes, so most of you did it correctly. So what we want to do is the usual thing. We change X like that, and we see what would be the variation of this term. Let's call it SQ. So delta of X SQ, it will have two terms. There will be the variation of this X mu, so there will be delta D of X mu is sigma times A mu, and then there will be another term because A mu is a function of X. So we have A mu of X plus delta X, which can be Taylor expanded because delta X is an infinitesimal. We can Taylor expand this to write it as delta X mu d mu A mu, and then we ignore higher order terms because we want to linearize delta X. And now I'm just looking at the terms which are proportional to delta x, so this term I don't care about. The variation has this additional term, delta x mu d mu a mu. Now, as before, we have derivative of the variation, and whenever we have derivatives acting on the variation, we do integration by parts so that we can factor it out, like here or here. So we factor out we want to factor out the variation and use the fact that it's arbitrary to say that what multiplies the variation has to be 0. So here we do an integration by parts with respect to this sigma, and use the fact that delta x vanishes at the boundaries of the integral. So this first term, after integration by parts, it gives me delta x mu d by d sigma of a mu, and the second term is what it is. I can do something. I can rename these indices. So I can rename mu to be mu and mu to be nu, because these are called dummy indices. They are summed over, so it doesn't matter what I call them. So I call this mu. I just rename mu by mu. But we should be careful with the contraction. So the index of delta x is contracted with the derivative of a. So delta x mu becomes d mu, and then here I have a mu.
You have a minus sign in the first term?
Oh yes, thank you. And then there will be total derivative terms, or boundary terms. Okay, now it has a usual form. So there is delta x mu multiplying something. Well, this thing. So if I want to write the equation of motion, so we had these two terms. There was this term, the variation of the free part, the length of the curve. And then we have that, we combine them together, and the whole thing should be equal to 0. Now I should keep this factor of m. So what do we get? We get m times d by d sigma of dx mu by d tau. And from this second term, we get minus q d by d sigma of a mu. Or let me call it plus q minus d by d sigma of a mu plus dx mu d sigma d mu a mu equals 0. Now we can write this d by d sigma of a mu. We can write it in terms of derivatives of a mu and the velocity of the field, because a mu depends on sigma through x mu. So a mu is a field, a function of x, and the reason we have non-zero d by d sigma a mu is because we are evaluating a mu along the word line. So this is d by d sigma of x of sigma. So this is equal to d mu of a mu dx mu by d sigma by the chain rule. So if I combine it here, I get m d by d sigma of x mu dot plus Q times dx mu d sigma multiplying d mu a mu minus d mu a mu equals 0. So this combination, this antisymmetric combination of derivative of a mu is called f mu, the field strength. And okay, what another thing that we can do is that to multiply the whole thing by the sigma d tau. So if I also multiply the whole thing by the sigma by d tau, this derivative becomes a derivative with respect to tau, and this becomes d by d tau x nu. So what we get is m x mu double dot equals or plus q x mu dot times f mu nu is equal to 0. Which is a familiar equation. This is, yeah, maybe one thing that we should do is to look at this equation in the rest frame, or look at the non-relativistic limit of this equation. That will be instructive, because, for instance, if I go to the rest frame, what is x dot nu in the rest frame? So this is a 4 vector, right?
Yes. The
mu.
three components will be 0. And the other one will be 1.
So this is what we call for velocity, right?
So 1.
It's 1, 0.
So it is 1 for the zeroth component and 0 for the spatial component. So if I look at the, if I go to the rest frame, the only non-zero component of this equation, this x dot nu, is the zeroth component.
Yes.
So what we get in the rest frame is mx double dot mu, or rest frame. Mu is plus q dot times f 0 mu is equal to 0, right? Because the only non-zero component of is mu 0. But since f is totally antisymmetric, the only the only non-zero components of this would be when mu is a spatial. So when mu is I get m x rest frame double dot I, also known as the proper acceleration, plus q fi 0 equal to 0. But this q fi 0 is nothing but the, sorry, fi 0 is nothing but the electric field, the ice component of electric field.
Yes.
So I get the usual fact that for a charged particle at rest, the force is q times e, perhaps with a minus. While if it moves, then there will be I components, so there will be ij components, and then ij component fij is related to the magnetic field. So if the particle moves, there will be also force due to the magnetic field. Okay. So let's move on to symmetries and nodal theorem. So when do we have symmetries? We have symmetries when we have an action which is invariant under some transformation of the field. So if we consider, for instance, this simple example of a point particle, no, not point particle, a scalar field. Imagine our scalar field does not have a potential. Then we say that this scalar field has shift symmetry, or this theory has shift symmetry of phi. So what is the general prescription? The general prescription is that I have some action. Yeah, let's just consider the general case. I have some action which is written as integral of some Lagrangian density. It depends on some variables or some fields, or maybe x in that example. And under some symmetry transformation, so let's say it's a function of, let's say phi stands for all possible fields in our theory, just a schematic. And I have some transformation of this phi field, some particular transformation of phi, under which delta S change of the action is a total derivative. So it's given by d for x d mu of some lambda mu. If this is the case, then we say this transformation is a symmetry transformation. Now examples are, for instance, if I have this scalar field without a potential, then it has a shift symmetry. So if I send phi to phi plus a constant, then how does the action change? So delta of S of phi plus some constant, that is equal to minus well, the change of the action is basically what is it? Does it change?
No.
It's zero, right?
Yes.
Because
The derivative of
this is minus, say this c is much less than 1 or less than 5. Then if I do it infinitesimally, or I don't even need, so this is d mu of phi plus c, but since I'm acting by derivatives and c is a constant, then this is equal to the original action. So this is a special case in which this lambda mu is 0. There can be more non-trivial cases in which lambda mu is not 0. So for instance, let's take the same action but consider some space-time translation. So say if x mu goes to x mu plus some a mu, then under this translation, the phi field, so phi is a scalar field. The way it changes, that phi goes to phi plus a mu times d mu of phi. Now let's plug this back in the action. So as what is delta A of S, and that is equal to minus 1/2. Well, there are two terms, so minus integral d for x d mu of phi, d mu of delta phi, which is a nu d mu phi. So since a is a constant, phi, this is equal to minus 1 over 2 integral d for x a nu of d phi squared. And since a is a constant, I can also write it as 1/2 d for x d nu of a nu d phi squared. So this is exactly how the formula that I wrote here. It's the total derivative of something, which reduces to a boundary. So therefore, this is a symmetry of the theory. So what is the implication of, any question about this?
Why is it minus? Why is it minus?
Where? Why do I put a minus here? In order to get positive Hamiltonian.
Oh, okay.
Because my metric eta mu nu is minus 1, 1, 1. So if I take this action, if I write it in terms of time derivatives and spatial derivatives, this is going to look like integral d for x 1/2 integral d for x phi dot square minus grad phi square. Right?
Wow, and the other,
Then,
the other way. The other way?
No. There is, this is the 0, 0 component.
Minus 1.
Yeah, but there is a minus.
Okay.
I thought that's what you are asking.
Yes.
You asked why do I put a minus? Because I want to get a positive sign for phi dot square.
Okay.
And then we can follow the same procedure to go from Lagrangian to Hamiltonian. We can derive the momentum conjugate to phi by doing the variation of the Lagrangian with respect to phi dot. That says that pi is phi dot. Then once we know pi, we can calculate the Hamiltonian the usual way, and with this sign, you get a positive definite Hamiltonian. So that's the reason.
Okay.
It doesn't change the equations of motion. Okay, so what is the implication of having symmetries? One important implication is that it gives us conservation laws. So we find quantities that are conserved, like for instance energy conservation. That is a consequence, or it can be thought of as a consequence of having time translation invariance. So another theorem is a theorem, or is a procedure to derive conservation laws starting from symmetry. So now we have some examples in which we had an action with a symmetry. Now we want to go through another procedure that gives us associated conserved current to this symmetry. So what is the idea? The idea is that we started from some particular symmetry transformation. Now the procedure, the trick to find the conserved quantity is to modify that symmetry transformation by multiplying it with some run with some localized function, arbitrary function. So imagine now I consider this other transformation. This is an altered symmetry transformation in which I multiply this delta S phi by some function epsilon with the property that epsilon vanishes at infinity. But remember that that didn't have to be the case here. So when we were doing variation principle, we were saying that delta phi has to vanish when we impose the boundary conditions. When I'm talking about symmetries, that doesn't have to be the case. So this delta phi that I'm talking about here, that doesn't have to vanish at the boundaries. For instance, in this example that I mentioned, it does not vanish. So here, this delta phi is a constant. It doesn't vanish at the boundaries. Also here, this A is a constant. So if phi field does not vanish, also the variation here will not vanish at the boundary. So this delta phi S does not have to vanish at the boundary. It might in some cases, but there is no requirement. Now here is the trick to derive the conservation that this epsilon does vanish at infinity. So it's some arbitrary localized function. Okay, so let's consider variation of the action under this transformation. So how do we expect it to look like? We expect it to look like something like this: d mu of epsilon times some 4 vector plus terms which are total derivative. So can someone explain why this is the form that we expect?
Because we're expecting the charge to be conserved. The current J mu. So
Yeah, that's what we want to prove, but yeah, I mean that's where we are going. But from the things that we saw before, it follows that if I consider the variation of the action under this, it has to look like this, assuming that this delta S of phi was a symmetry of the action. Down the field, right?
I don't know, maybe the only thing that can change is the epsilon. And because phi is a symmetry, so the only thing that can change the action is the epsilon. So we are taking the variation of epsilon with respect to, we're taking the variation of the epsilon with respect, the change in epsilon will make the change in S.
Yeah. So that is kind of the answer. So let me ask you this: imagine epsilon was 1. Then what would be the answer? Imagine epsilon was a constant.
total derivative as before?
Exactly. So if epsilon is not a constant, then the result can change, but it can only change because epsilon is not a constant.
Yes.
So anything apart from a total derivative has to be proportional to the derivative of a epsilon.
Yes.
Right? If epsilon is a constant, this term vanishes and I get a total derivative. Okay, so it has to look like this. Now let me just do an integration by parts. So we already have a total derivative sitting there. We can get some more total derivatives. But this first term is going to look like minus epsilon times d mu of j mu plus, again, some total derivatives. I don't write it anymore. Plus total derivative. Okay, now this epsilon is an arbitrary function that vanishes at the boundaries. Now this term again should look familiar from what we have been doing before. So remember, we were doing variations of the action with some arbitrary delta phi that vanishes at the boundary. We said that if we say the action, if the action is stationary with respect to variation, then what multiplies that variation should be zero on the equations of motion. So here we are doing exactly the same thing. We are doing some arbitrary variation because epsilon is arbitrary. We factored out epsilon. What multiplies epsilon, it has to vanish on the equations of motion. So what we conclude is that d mu j mu on the equation of motion, we call it unshelled. Unshelled means that when the equations of motion are satisfied, that has to be zero.
Can you repeat the first part, please?
So I'm saying that this transformation is one particular transformation that vanishes on some specific variation, right? That vanishes at infinity. Now we said that if we do variation of the action by something that vanishes at infinity, the action would be stationary with respect to that when the field satisfies the equation of motion.
Okay.
So in order for that to be true, this d mu j mu should be zero because epsilon is arbitrary.
But I'm still confused about the epsilon. What is that? I mean, why did I introduce there with the variation? I mean, splitted this into del s phi and epsilon.
Well, because I wanted, so let's look at this object, epsilon of x delta s of phi.
Yeah.
Right? So remember at the beginning we were talking about doing variations of the action. So what were we doing? We were saying that take phi to phi plus some delta phi, which is totally arbitrary,
Yes.
except that it vanishes at infinity.
Yes.
Now this object satisfies those requirements. It's some arbitrary variation that vanishes at infinity.
Yes.
So I introduce epsilon so that this is a particular form of a general variation.
Okay.
So for those, I know what happens. I know that on shell, the action is stationary. So any variation that vanishes at infinity should multiply the equation of motion, or something that vanishes on the equation of motion. That's the role of epsilon, to make this variation something that is compatible with what we were doing when we do variation. Delta S of phi, on the other hand, does not satisfy that generally. exactly because of what I said here. This delta, this symmetry transformation does not have to vanish at the boundaries. So, for instance, if I change it by constant, that definitely doesn't vanish at the boundary.
Yeah.
So it's not an arbitrary variable. The usual variable, it doesn't satisfy the conditions for variational principle.
Yeah.
So epsilon is there so that I satisfy the condition for variational principle. And then I can make statements about when the fields are on shell. But this is only valid on shell, but when we have a symmetry transformation, the action is invariant. Here, I never use any on-shell condition. So on-shell condition comes from the fact that I'm considering this epsilon that vanishes at infinity. And then I use the usual definition of being on-shell. Okay, so let's look at the example. I think that is useful. Okay, I'm going to do two examples very quickly. The same two examples. So for the case of phi shift symmetry, what we are going to do is to take phi to phi plus some epsilon of x times c, but we can just take c to be 1. If c was a constant, right? It wouldn't matter, we could just take it to be 1. So it's just phi going to phi plus epsilon of x. So here is the example of, so here we are looking at the massless field. What is the variation of action on this transformation? So this is again minus integral d for x d mu of phi, and then now when I plug this in, so before, remember what happened was that the variation of the action was 0 on the constant shift. Now when I change this parameter from being a constant to epsilon times a constant, where epsilon is not a constant, then I get exactly the form that we were expecting. Or maybe I should put the indices like that. So this is exactly of the form that we were expecting. This does not vanish because epsilon is not a constant. And then I can do integration by parts to get epsilon times d mu of d mu phi plus the total derivative. So the conserved current J mu is just d mu of phi, or if I want to use the metric, is this. And obviously on shell it is equal to 0. D mu or J mu is just the D'Alembert of phi, which is indeed equal to 0 on shell. So another thing where I invite you to do this exercise. This theory, this scalar field theory is also invariant on the linear shifts. This is a bit less trivial, where B is a constant 4 vector. So you can, as an exercise, you can try to derive J mu of B and verify that it satisfies this condition. since it is late. But maybe we can do it tomorrow. Okay, maybe I derive T mu nu. Yeah, what is good for doing tomorrow? But you can look at the notes for derivation of T mu nu using the same idea. So we can this symmetry on the translation gives us a current that is the stress energy tensor. So you following the same procedure, you can derive the stress energy tensor. You can see it in the notes, and tomorrow we can discuss it if there is some question. One last thing that I wanted to mention today is that we can, when we have conserved currents, we can define conserved charges by integrating the zeros component of the current over the whole space-time. Sorry, over the whole space. So I do some constant time slice and integrate J0, and this Q is time independent because of the conservation of J mu. So this equation can be written as d by dt of J0 plus di of Ji is equal to 0. So if I take the time derivative of Q, that turns into d0 of J0, which is equal to minus d3x di of Ji. So if this integral is over the whole space, and if there is no flux at infinity, then this will be 0. So therefore Q is a constant charge. Okay, I can stop here. I graded the homeworks. They are here. Any questions? No. So see you tomorrow at 2.
Who is it? I can't find the note. Okay, it's not Lagna, so you will get good grades.
There is no
There are grades, but it's
This is the highest grade I ever get in homework. Because I didn't do the problem 3.
If you're failing, you're gonna fail more.
in the final. You're studying your final.
I'm not
You're the one who wrote.
But he has a unique approach here.
Tú eres historiador como Pablo.
Let me see that.
Thanks.
Something unique.
I slept.
Yeah, I saw it.
You already know that. My time is messy, so I'm the one who is tired. Okay?
But still, I didn't miss the
Of course.
Yes.
It's not that stupid.
Sí, pero
No one
sí,
will
podríamos
see.
ir.
I go far.